In chapter 15, we were talking about reaction mechanisms, but there's one kind of mechanism we really can't deal with until we get to chapter 16, which is equilibrium. And that is a mechanism in which we have a fast equilibrium in front of a slow step. So what is the rate law for a reaction that looks like this? Well, back in our study questions, we have a nice question like this, and it's talking about ozone decomposition. So the questions are asking kind of lead us through the pattern, and that is, what is the rate determining step? And that's pretty easy. It's our slow step, in this case the second one. What is the rate equation for the rate determining step? And then finally, what is the rate equation for the overall reaction? So let's kind of zoom in a little bit closer here. So we know our rate determining step is the slow step, the second step. And for this, the rate is going to be the rate law will be the rate law for that slow step. So it's going to be rate equals K times the concentration of ozone, O3, times the concentration of oxygen, like that, single oxygens, and both of those, since it's a 1 and 1, it's going to be first order for each of those two. Now that would be the rate law for the slow step. But the rate law for the overall equation, okay, has to take into account the fact that when we put these two equations together, that these oxygens are actually going to cancel out. In fact, the overall reaction we can see is going to be two O3s, okay, are going to turn into three O2s. So, how do we deal with this? What we do is we take our first step up here. Let me kind of clear off some of the things I've drawn. That the first step is an equilibrium. And at this point here, we know that equilibrium, KEQ, is equal to the concentration of the products. So that's O2 times the concentration of O all over the concentration of O3. So that's a chapter 16 idea. Now, we're going to use that here. We're going to substitute in for our O. So we're going to take this rate equation and we're going to change it around, and I'll do it in green, so that my concentration of O, we can see, is going to be equal to our constant, okay, K from KEQ, times concentration of O3 over concentration of O2. So you can see that all I've done now is just solve for O, and by putting my O3, multiplying both sides by O3, dividing both sides by O2, I come up with this expression. And I'm going to go back and I'm going to substitute this into my original equation. And you can see what I'll have. I'll have rate equals K, concentration of O3, and now substituting it in, I can have another constant K times the concentration of O3 over the concentration of O2. So when I'm all done, this is a constant and this is a constant. So if I multiply them together, I'm going to get another constant. So this rate, and here's our rate law for the overall reaction, equals a new K, which is just my old K multiplied by my equilibrium constant. So constant equals constant. O3 times O3, so O3 squared divided by O2. A little crowded here, but that would be my answer for what is the expression for the rate for the overall reaction. Now here's from a Nacho question, same idea. So we can see where we have my fast equilibrium and my slow step. So the constant for the rate for the slow step is equal to K times the concentration of C. Okay, but I go back to my first step and say, okay, the equilibrium constant is concentration of C divided by the concentration of A times the concentration of B. And if I want to solve for C, I can see my concentration of C is equal to K times the concentration of A times the concentration of B. So I'm going to substitute this C in for this C, and you can see what we get as the final answer here is rate is equal to a little k and a big K, concentration of A, concentration of B. So these are going to turn into a new constant. So you can see my answer is going to be C. So the rate of this equation, this mechanism, would be K times the concentration of A times the concentration of B. Now this again has shown up in FRQs from time to time on the AP exam. So we can do the same thing. Here's our fast equilibrium. So that's going to be the KEQ is equal to the concentration of AB divided by the concentration of A and the concentration of B. We can see that the rate law is the rate of the slow step. So the rate of the slow step is rate equals K times AB times B. Now AB is an intermediate, so that's going to go away. So I'm going to substitute in for AB. So I'm going to take my expression over here, my red, and say the concentration of AB, actually I think that means intermediate AB, is equal to a constant times A times B. I'm going to substitute this in for here, and my final answer will be rate equals, okay, little k, big K, we're going to multiply those together and just call it K, times the concentration of A, times the concentration of B, that's from here, times the concentration of B, which comes from there. So I've substituted in this AB for this AB, and I have a new rate law. I'll write it one more time to be clean. Okay, this K, and I can call it K prime if I want. Okay, A and 2B, so concentration of A times the concentration of B squared. This would be my answer. Now, if you look at this reaction, you can kind of see, well, we could sort of say, what if I just took this and said this equals AB and substituted in here? I get A plus B plus B, and that turns into A and B to the second order, sort of like this. Okay, which kind of gives you the right answer. If you're doing a quick multiple choice question, then you can just kind of think of this as an algebraic equation. But on FRQ, where you want to go back and say, why is this true? Then we use the KEQ expression for the fast step, and then the rate law of the slow step, and we substitute in that expression, and we get our answer.